So I know I'm kind of repeating myself here, but these are important ideas. At equilibrium, the rates of the forward and reverse reactions are equal. The rates, not the concentrations. That does not mean that the concentration of the reactants is equal to the concentration of the products. It could happen, but it's very unusual. Usually they are different. Well, what can we know about the the concentrations of reactants and products? There's something called an equilibrium constant that allows us to quantify the relative concentrations of reactants and products at equilibrium. So if we consider a generic chemical equation, so lowercase a represents the coefficient of reactant A, and lowercase b the coefficient of reactant B. This is a reversible reaction and it's forming C and D, and these also have coefficients. We can write, we can talk about an equilibrium constant, and this is a ratio of concentrations of products to concentrations of reactants. Ratios can be expressed as fractions. So we've got the products divided by the reactants. When we put the chemical formula in brackets like this, it means concentration of. So the concentration of C, and that is raised to a power equal to the coefficient. We'll do an example. It'll make a little more sense. So let's look at a real reaction, not a generic one. So here we've got 2N2O5 decomposing to form 4NO2 and 1O2. To write the equilibrium expression for this, we're going to take the products, NO2 and O2, and we're going to write them in brackets indicating the concentrations. Then we're going to look at the coefficient. This one has a coefficient of 4. So this concentration is raised to the 4th power. This has an implied coefficient of 1. And so this would be raised to the coefficient of 1, exponent of 1. Do we need to write that? No, anything raised to the 1st power is just itself. And that's divided by the concentration of the reactants. Well, there's only one reactant. It's N2O5, so we put that down here in brackets. It has a coefficient of 2, and so we square that. So the coefficients are becoming the exponents. This is not some arbitrary thing we thought up. This is actually descriptive of what is happening, and there's a lot of chemistry behind this that we don't have time to go into. So you'll just have to take my word for it. So let's practice doing this. Write an equilibrium expression for this chemical equation. So KEQ is going to be a fraction. We're going to take the product. What's the product? 2HF. So the formula for the product is HF, and we're going to put that in brackets. And what do we do with the 2? Yeah, it becomes a superscript or an exponent. It's not 2 plus, that would be a charge. Here it is 2, which just like in math means squared. So this is the concentration of HF squared. And then down here in the bottom, we're going to take the concentration of each of the reactants. So H2 in brackets and F2 in brackets. And then we look at their coefficients. What are their coefficients? Unwritten ones. So we'll use exponents of unwritten 1. And there's our equilibrium expression. Any questions? This is just, it's not necessarily difficult, it's just kind of weird and strange, huh? Make sure I didn't miss anything. So what we'll often see is something like this. Here's an equilibrium, The double arrow means that the reaction goes in the forward direction and in the reverse direction. And then over here it says KEQ equals 1.9 times 10 to the 19th at 25 degrees Celsius. That's a really big number, isn't it? That's a 1 and a 9 with 18 zeros. That's a really, really big number. Well, what is the equilibrium expression, for this first equation? KEQ is going to equal what? HBr, and the 2 becomes the exponent, right? And then down in the bottom, what do we have down here? H2 and Br2. Any exponents on those? They're 1s, so we don't have to write them. So if this expression is equal to this really, really big number, does that mean the numerator is bigger than the denominator? If we take a big number and divide by a small number, we get a bigger number, right? If we take a small number and divide by a big number, we get a small number. Does that make sense? Yeah, you guys are zoning out on me, aren't you? It's okay. I'm zoning out too. If this is equal to a really big number, like 1.9 times 10 to the 19th, that means that the top of this expression has to be a lot bigger than the bottom. That means that the concentration of the product must be a lot higher than the concentration of the reactant. That tells us that this reaction goes mostly in the forward direction. Down here, KEQ is small, 4.1 times 10 to the minus 31. I think small is an understatement. That's incredibly small. KEQ for this one is going to equal NO squared, right, divided by N2, the concentration, and O2. So if this is equal to 4.1 times 10 to the minus 31, which is bigger, the top or the bottom? The bottom must be bigger in order for this to be such a small number. That means that for this reaction, it goes mostly in the reverse direction. The concentration of reactants at equilibrium is going to be higher than the concentration of the product. Does that make sense? So here's pictures for the same stuff. So here's that reaction, hydrogen plus bromine forming 2 hydrogen bromides. And here we have a picture at equilibrium. KEQ is the concentration of the product squared divided by the concentration of each of the reactants multiplied. And what do we see here? What do we have more of, reactant or product? We have more product. These are the products. There's a lot of those, and there's not much of the reactant, because this is a large number, meaning the top must be bigger than the bottom. This is the opposite situation, small equilibrium constant. N2 plus O2 making 2NO. Small number, so what's on the top must be smaller than what's on the bottom. And we look at the picture and we see that there's very little product. There's a product molecule, there's a product molecule, but most of it is reactant. So the equilibrium constant tells us which direction the reaction favors. It tells us which side the products, the concentrations will be higher. So if the equilibrium constant is much smaller than 1, the reverse reaction is favored. The forward reaction does not proceed very far. If the equilibrium constant is roughly equal to 1, anywhere close, then it's more equal, the forward and reverse reaction. and we'll find that there are significant amounts of both reactants and products at equilibrium. If the equilibrium constant is much larger than 1, that favors the forward reaction, and there's virtually no reverse reaction. Any questions?